Hello. I would like for us to work through the section 3.2 notes, which is going to cover two topics, Rawls theorem and mean value theorem. So I kind of just want to do a brief introduction of both of them before we start looking at them, just so that you can see what the difference is between the two of them. So in the last section, we looked at the extreme value theorem, which says if I have a continuous function on a closed interval, that I guarantee that there will be an absolute max and an absolute min in that interval. But if you remember that there were times that we saw that, let's say I've got my function and I'm looking at this interval, that it's possible that if it's strictly increasing or strictly decreasing, that those max and min values occur at the endpoints, right? So there was a French mathematician named Michel Rolle who came up with this Rawls theorem that would give conditions that guaranteed that that max and min would occur in the interval, not at the endpoints, but within the open interval. Again, so that excludes the endpoints. And so Rawls theorem is going to say something to the effect that if I have a continuous function that's on a closed interval and it's differentiable in the open interval, then, and also that the endpoints of the interval have the same value, right? Then I guarantee that somewhere within the interval is where I'm going to get my max and my min. And again, we're talking about a max and a min, so the tangent line there at each of those 2 points is 0, and that is also the slope of the line, the secant line that connects the two endpoints, right? So again, this theorem, the Rawls theorem, is related closely to the extreme value theorem, but what it does is it guarantees that the max and the min are going to occur within the interval. And again, we'll know that basically it's saying that the slope of the secant line that goes through A and B will share the same slope as the max and the min values, which should make sense because the slope of the tangent line is always going to be 0 when we get to a max or a min. All right, contrast that with the mean value theorem, which takes away the requirement that f of A and f of B have to be equal. All right, so we've got f of A and let's say f of B here. All right, we still have a continuous function on a closed interval. It's differentiable on the open interval, but what it's saying from a geometric point of view is it's saying that the slope of the secant line, which is now no longer 0, right, because f of A and f of B are not equal, the slope of the tangent line will match the slope of the tangent line at some point in the interval. Right, so from a geometric perspective, it's just saying that there will be some point within the interval whose slope matches the slope of the secant line through A and B. But from a, I guess more an analytical perspective, what it would say is that this right here, which we would call the average rate of change over the interval. Again, we talked about that, I think in chapter 2, we said that that average rate of change is f of B minus f of A over B minus A. That was the average rate of change. And so what it's saying is that there is some other point in there whose instantaneous rate of change will match the average rate of change over the interval. Right, so again, the major visual difference is just that f of A and f of B have to be equal in Rawls theorem, and in mean value theorem, they don't require that, and it changes it so that we've got, you know, the average rate of change here is equal to the instantaneous rate of change, or the slope of the secant is equal to the slope of the tangent for some point in that interval. Okay, so let's take a look at what specifically the theorem says, and then we'll do a couple of examples. All right, so let f be continuous on a closed interval AB. It starts out exactly the same way as the extreme value theorem did, and differentiable on the open interval. Again, we also said that on extreme value theorem. And then it says if f of A equals f of B, then there is at least one number C in the open interval such that the derivative is also 0. And again, that guarantees that that max or min is occurring within the interval, not at the endpoints. Okay, let's take a look at that. So find the two intercepts of x squared minus 3x plus 2 and show that the derivative is 0 at some point between the two intercepts, the two x intercepts. All right, the reason that they're asking it this way is because they want us to find the 2 points which will have that the f of a and f of b will have the same value. If they are both crossing the x-axis, then clearly f of a and f of b will both be 0. And then we'll choose that for our closed interval. So first thing is we're going to find the two intercepts of that, and then we'll go back and we'll talk about the continuity, the interval, the differentiability. All right, so find the two x-intercepts of f of x equals x squared minus 3x plus 2. All right, so I'm going to set that x squared minus 3x plus 2, and I'm going to set that equal to 0 so I can find the intercepts. All right, I think I get x minus 2 times x minus 1. And that gives us the two intercepts x equals 2 and x equals 1. All right, so again, here it said basically we have some closed interval. Here we've had to decide that that closed interval is going to be 1, 2, because those are the 2 points that we can guarantee that f of a, in this case f of 1, and f of b, which is f of 2, are both equal, and because they're the intercepts, we know that they both equal 0. All right, since we have found that, we now have our function on a closed interval. Let's check the other condition. So f has to be continuous on that interval. All right, so is this continuous on the closed interval 1 to 2? Yes, all polynomials are continuous everywhere. Is it differentiable on the open interval? Well, again, yes, all polynomials are differentiable everywhere. And then the third requirement is that f of a equals f of b. In other words, f of 1 equals f of 2, which we just established. All right, so we can use Raoult's theorem. So again, f is continuous. I kind of need you to just go through all three of these requirements. F is continuous on the closed interval. F is differentiable on the closed interval, and f of a equals f of b as the endpoints of those two intervals. Okay, so then Raoult's theorem says that there is at least one point in the open interval, 1, 2, such that the derivative is 0 there. All right, so since they're telling us something about the derivative, we need to take the derivative. So we've got f prime of x is 2x minus 3, and it's telling us that somewhere in this interval it will equal 0. All right, so we subtract 3 and divide by 2, and we end up getting x equals 3/2. Just double check to make sure that that's in the interval, because on occasion we'll find that there are other places where the derivative is also 0. Raoult's theorem is only talking about within this interval right here. So 3/2, 1.5, that's definitely within that interval right there. Okay, so then we found it. So there is some point, so the point 3/2, comma, let's find out what the y value is for that. 3/2 squared is 9/4 minus 3/2 times 3 plus 2. So 9/4 minus 9/2 plus, I'm going to change this to 8/4, and then we'll change this to 18/4. So that's -9 plus 8 is -1. So -1/4. The point 3/2, -1/4 has a horizontal tangent line. Or let's say the horizontal tangent line at the point 3/2, -1/4, has a slope of 0. Well, wow. Okay. This is where I wish I could do edits. All right. There is a horizontal tangent line. Horizontal tangent line at 3/2, -1/4. Sorry about that. Okay, And we know this is a parabola, so let me just show you what that looks like. So it's got its intercepts at 1 and 2, and it's just going to go something like this, where it's going to have its y-intercept at 2. So it's going to look something like this. And we can see there that at that point halfway between the two of them, it will have a horizontal tangent line. Okay, let's do the same thing for this new function here, f of x equals x to the fourth minus 2x squared. Find all the values of c in the interval, the open interval, -2 to 2, such that f prime of c is 0. So again, to use Rawls' theorem, we need to check three things. One is f is f is continuous on the interval, f is differentiable on the interval, and in this case, specifically, we're looking is f of -2 equal to f of 2. So let's go through and check those first before we just, willy-nilly go and apply Rawls' theorem. All right, so f is continuous. Again, hopefully that's an easy one because this is a polynomial. F is differentiable. Again, polynomials are continuous and differentiable everywhere. And then we need to show that f of -2 equals f of 2. Again, they gave us an open interval, but we could easily say it doesn't matter whether they give us open or closed. F is continuous everywhere, so it's also continuous on the closed one. It's differentiable on the open one. All right, so now f of -2 and f of +2. So if we put -2 in here, we get -2. Whoops. -2 to the fourth minus 2 times -2 squared. Right, -2 to the fourth, 2, 4, 8, 16, that would be +16 minus 2 times 4. So in other words, 16 minus 8, which is 8. And we do the same thing for f of 2, and we're going to get the same thing because this is an even function. So when we do 2 to the fourth minus 2 times 2 squared, we end up again with 16 minus 8, which is 8. So is f of -2 equal to f of +2? Yes, it is. Okay, so then now we are allowed to apply Rawls' theorem, which says that the derivative of this is equal to 0 at some point in this interval. All right, so we've got f prime of x equals 4x to the third minus 4x. And I'm going to set that equal to 0. I'm going to factor out a 4x here. Whoops, I said 4x, and I just did 4x. And I end up with x squared minus 1 equals 0. All right, this factors more, so we've got x plus 1, x minus 1. So I have a product of three things equaling 0. One of them has to be 0, so I end up with x equals 0, x equals -1, and x equals +1. And again, just as we said in the last example, we need to check to make sure that these are in our intervals because they might not be. They might be places where the graph has a horizontal tangent line that's not even in that interval. So is 0 in our interval -2 to 2? Yep. Is -1 in there? It is. And is 1 in there? Yes, it is. Okay, so then we will have three extrema in this interval where we've got these 3 points. So let's find what the y value is for each of them. So if I plug in 0, I get f of 0 is equal to 0. So this point is going to give us 0, 0. If I plug in -1, again, this is going to be the same for +1. If I plug in -1, I end up with -1 to the fourth minus 2 times -1 squared. That is 1 minus 2, so that's -1. So this is going to give us the point -1, -1, and this is going to give us the point -1, +1. So at these 3 points, we have horizontal tangent lines. All right, so let me just sketch what this one looks like for you. It is a quadratic, and at 0, it's 0. At -1, it's -1. At +1, it's +1. It's a quadratic. Again, we know about end behavior here, that when it is an even exponent, either they're both going to go towards infinity in the positive direction or negative infinity. But here, since the coefficient's 1, it's heading towards positive infinity. All right, and then we're going to come in here and do that. So it's going to look like that. And again, we see those spots in here where we are going to reach our max and our relative max and min. Okay, next set. Now, mean value theorem, again, is removing a requirement that f of a has to equal f of b. But it does add something at the end that's going to make it a little bit more work. So at the beginning we have less to check, but at the end our checking how we find that c is going to be a little bit more difficult. All right, so again, we have f has to be continuous on the closed interval. It has to be differentiable on the open interval, same as Rawls' theorem. But again, it does not require f of a to equal f of b. And what it says is there is a number, c, in that open interval such that the slope of the tangent line at c is equal to the slope of the secant line that goes through a and b. Right, so again, our diagram was something like this, where we've got a here and b here. And again, let's say this is f of a and here's f of b, that it could do something like this. We don't know what it is, but we're just saying here is the slope of the secant line that goes through a and b. And somewhere in there, I'm going to guess maybe right about here, we've got a point C down here where the slope of the tangent line matches the slope of the secant line. So here, this is going to be easy for us to find that, the slope of the tangent lines, just through the derivative. But here we're actually going to have to use that slope formula, all right? That is a part, I think, where people kind of tend to get a little bit stuck or frustrated with mean value theorem because they're like, now what do I do when I find the derivative? What do I set it equal to? So we have to have a step in here where we take the time to find the slope that goes through those points. Okay, so here we have a function here, f of x equals 5 over 4 minus x. Find all values of c in the open interval 1 to 4 such that f prime of c equals f of 4 minus f of 1 over 4 minus 1. Again, don't look at this as anything necessarily other than just the slope of the line that goes through x equals 4, or yeah, where the ordered pair is 4 comma something, we don't know what that is yet, and 1 comma something, right? So it's the slope of that ordered pair. Okay, now you might be thinking, oh goodness, is this continuous? I have a spot where there is a variable in the denominator. So we're just going to look at that and say, okay, yeah, it's not continuous when x is 0. But then we look at our interval and we say, oh, okay, shoo, they aren't looking at that spot where the function's not continuous. 0 is to the left of the interval, all right? So yes, it is continuous on the closed interval 1 to 4. It is differentiable on that spot. Again, this is going to look something like, well, let me see, I have it sketched right here. It's going to have an asymptote at 0. It's going to have a vertical asymptote right here. And then, let's see, at 4, it crosses over at 1. Sorry, at 4, this is 1, so 5 minus 1 is 4, so 1, 2, 3, 4. It's going to be up here somewhere. It's going to come down and do like this. Let's say at 1, it's 1. Yeah, so it's going to do something like this, right? But again, we're only concerned about this interval from 1 to 4 right here. So again, that part that's a problem is not even in our vision at this point. Everything looks cool with where we are right now. Okay, so then let's figure out what this is right here. I always try to do that first because it's the thing that's so bothersome to me. So first thing we need to do is find out what is f of 4. We already did that actually. It's 4 because if I do 4 over 4, that's 1. So 5 minus 1 is 4. So f of 4 is equal to 4 and then f of 1. So years ago, when they first got E-ZPass, this was a concern that everybody had, that you would be able to track how fast people were going. And that's turns out that nobody ever got busted for that, but that was definitely a concern. So we have 2 stationary patrol cars equipped with radar, and they're 5 miles apart on a highway, as shown in the picture on section 3.4 on page 185. So we've got these, I'll just sketch what it looks like. So we've got 2 police cars. We'll put one right here and one right here, and they are 5 miles apart. All right. So a truck passes the first patrol car. We're assuming that they're heading in this direction right here. As a truck passes the first patrol car, so right here, its speed is clocked at 55 miles an hour. And then 4 minutes later, when it gets over here, the truck passes the second patrol car and its speed is clocked at 50 miles an hour. So it looks like it's actually slowed down. But if these 2 patrol cars are talking to each other and they say, hey, watch out for that, you know, that Target truck or that Amazon truck as it goes by, they would be able to tell how fast it was going through here. So proof that the truck must have exceeded the speed limit of 55 miles an hour at some point. Again, so all their evidence is right here is that it was going 55 here and 50 here. All right, so let's see what happens. So let t, oops, I was going to say let equal because I already wrote a t. Let t equal 0 be the time in hours when the truck passes the first patrol car. All right, so this is going to be t equals 0. All right, so we need to figure out time in hours again, because this is miles per hour. Otherwise, this would be completely different if we measured miles in minutes. But for right here, then it tells us that 4 minutes later is when it's passing this. So what is the time at this point? Think about that for a second. All right, we could say that it's 4/60ths of an hour, because it's 4 minutes out of 60 minutes, which is 1/15 of an hour, right? So t equals 0 here, t equals 1/15 at that point. At t equals 1/15 of an hour, it passes the second patrol car. Okay, now again, there's no function that they give us, so we just have to think of, you know, we're just going to call let s of t be the position function. And again, we're not going to have a formula for it per se, but we are going to use that to find the instantaneous rate of change within here. So what we're going to say is then we need to have, let's say, our average velocity is going to be s of 1/15, that's our greater time, minus, I almost did f, s of 0 over 1/15 minus 0. Again, that's our f of a minus f of b over a minus b. So that's what the average velocity is, right? And so what we're going to do is we're just going to find that at some point. We just want to know what's going on in there. All right, so its position at, well, let's say this, its position at time 0, that's this right here, is just going to be, again, we're assuming this is the starting point, so we'll say its position here is 0. And its position at 1/15 of an hour is when it's come all the way down here. And that is, it's gone 5 miles from our starting point. So here we're at 5 minus 0. And then we've got 1/15 minus 0. So then we end up with 5 over 1/15, And again, what we do with keep change flip there is we end up with 75 miles per hour. So again, if we knew what this position function looked like, what it's saying is that the average rate of change, the slope of that tangent line, or I'm sorry, the secant line that connects those 2 points would have a slope of 75, a rate of change of 75 miles per hour. And so what it's saying is that at some place in here, again, I totally am just doing this for a visual. We have no idea what this function looks like. But at some point, it's saying that there is a point between time 0 and time 1/15 of an hour where the average rate of change matches the instantaneous rate of change at some point in here. So what it's saying is that at some point in those 5 minutes, that truck must have matched that. In other words, its instantaneous rate of change would have been also 75 miles per hour. All right, so again, hopefully you can understand why people would be concerned once EasyPass came in, that maybe they would clock how long it took you to get from, you know, let's say Fort Washington to King of Prussia or something. But again, that hasn't happened. But this would be an application of it to find out that at some point you must have reached that same speed. Okay, there's one other thing in here, and that is a useful alternative to the mean value theorem. It says if f is continuous on the closed interval AB and it's differentiable on the open interval AB, then there exists a number C in that interval such that f of B equals f of A plus B minus A times f prime of C. That might look like it's coming out of nowhere, but let me just write this again, which we said before. F prime of C equals f of B minus f of A over B minus A. All right, that's what we said was required, that at some point, again, we have these conditions, f is continuous on the closed interval and differentiable on the open interval. Then at some point in that interval AB, there must exist a point C in there such that the instantaneous rate of change, or the slope of the tangent line, must match the average rate of change or the slope of the secant line. So if we take this and we multiply both sides by B minus A, all right, so I'm going to multiply this by B minus A, and we'll multiply this by B minus A. These will cancel, and I end up with f of B minus f of A equals B minus A times f prime of C. All right, and then if I just move f of A over to the other side, I get this condition exactly right here, or this, this value. So we've got f of B equals f of A plus B minus A times f prime of C. Again, we'll find times when that's useful, just like we found the alternate form of the derivative was very useful when we had things like absolute values. And so we'll talk about times when that would be useful to us. Okay, that's it.